Hello, my name is Jonas Friederich and I am a PhD student at the University of Southern Denmark. I'm now going to present you our paper, Experimental Comparison of Open Source Discrete Event Simulation Frameworks. First, let me walk you over the agenda. I'm first going to motivate this paper and going to introduce you to the research questions. Then I'm going to show you our search process, which we used to identify the relevant frameworks. Then I'm going to run you over the experimental simulation model we implemented for each of the relevant frameworks. And then I'm going to present you the results of our performance and usability comparison. Then I'm going to give an overall comparison of the frameworks before I finish this talk with a summary. So the motivation and research questions. The motivation was to compare among open source discrete event simulation frameworks by conducting a controlled experiment. This is done to provide guidance for researchers to make an informed choice on which framework to use. The research questions were: what open source discrete event simulation frameworks exist? How do they compare on specific parameters related to quality attributes in software engineering? And which frameworks perform best during runtime? This table basically resembles our search process. We used the academic research database Web of Science to identify frameworks for discrete event simulation. This resulted in 50 candidates for potential testing. We filtered out the candidates that are no longer actively supported by only considering frameworks that were at least last updated in 2018. The results were the 13 frameworks you can see in this table. After the filtering on dates, we analyzed the remaining 13 frameworks and identified the most important characteristics to give a more holistic impression of the overall collection of frameworks. For the domain, we gave a 1 to 3 score, with 1 being very domain specific, 2 allowing generic use, and 3 decidedly generic in its domain. The OS column refers to how many of the 3 most common operating systems, so Windows, Linux, and Mac OS, the frameworks are directly integrated into. For the extension category, we denoted frameworks with only manual custom extension with 1, and frameworks with specific mechanisms for extensions with 2. With license, we denote frameworks with 1 if no distribution is allowed, 2 if only non-commercial distribution is allowed, and 3 if the license is completely open. The engagement category shows the GitHub stars S and forking F score of the framework repositories. To get the 5 chosen frameworks, we set the domain and license score to be 3 and the engagement to maximum. SymPy is based on standard Python and can be described as a domain-specific library. It is specifically designed for discrete event simulation, but can be extended to include continuous simulation through custom extension in Python. It is distributed under the OpenMIT license, meaning all modifications and extensions are allowed, and it maintains an active and widely engaged community. SimJulia differs from SimPy in that continuous event processing is directly integrated along with discrete event processing, which is what we are interested in. It is technically quite similar to SimPy in that the API modeling imitates the one of SimPy. Its documentation and community engagement are extensive, and the licensing is identical to that of SimPy. YAMSim differs from SimPy and SimJulia in its method of simulation implementation, in that developers can use its IDE and integrated graphical input functionality. Beyond that, it is quite similar in supported functionality and, like SimPy, focuses directly on discrete event simulation. SSJ is a Java-based simulation framework whose primary focus is on discrete event simulation. As such, SSJ includes the expected tools and methods for developing standard discrete event simulation models. SSJ supports both continuous and hybrid simulation and allows developers to implement models in a variety of general purpose languages as well as simulation-specific languages. JavaSim is described as an object-oriented discrete event simulation toolkit, directly integrated with the general purpose Java language. JavaSim also supports both continuous and discrete event simulation. On this slide you can see the experimental simulation model. We implemented this model using each of the 5 frameworks. The simulation model emulates a street food-like scenario with 3 important aspects, namely customers are able to order multiple times, there is a limited amount of customers that can be in the street food at once, and the customers pay before they leave. We ran the model with increasing input loads and recorded performance indicators such as computational time and CPU usage. Furthermore, we conducted a usability comparison of the frameworks based on several factors. First, let's have a look at the results of the performance comparison. The top figure shows the average computational times for each framework. As mentioned before, each framework was tested under increasing load in the interval from 25 to 500,000 customers, with each interval having a range of 25,000 customers. Further, each interval was repeated 10 times to ensure the results would not be overly biased by outliers. Note that due to time constraints and the very evident degradation in performance under increasing loads, the tests for SimJulia were stopped at some point. The lower figure shows the average CPU usages in percentage across the tested input intervals. Note that YAMSim occupies a substantially greater percentage of the CPU for the lower input sizes, before gradually decreasing until it is around the level of the remaining frameworks. This is expected given the nature of the YAMSim framework, while the remaining frameworks are integrated directly into general purpose programming languages and could be described as simulation libraries in the given languages. YAMSim is a standalone framework. Let's have a look at the results of the usability comparison. We performed a usability comparison based on the factors startup documentation, best practice examples, extension options, errors during development, time to implement, and lines of code. Note that each score is given within a 1 to 5 interval. For all factors, 5 is the best possible score and 1 is the worst possible score. Startup documentation refers to a get started type of documentation, often found within the documentation of development frameworks. The same goes for best practice examples. Extension options refers to the intuitiveness and availability of methods to extend the framework with custom implementation. Lines of code shows the actual lines it took to implement the model. From the gathered parameters, an overall ease of use score was given by weighing each parameter equally. As can be seen, YAMSim, SymPy, and SSJ performed best during the usability comparison. Now let's have a look at the overall comparison. SSJ was found to perform the best across all intervals in terms of computational time, while utilizing a relatively high percentage of the CPU. It also received a good overall usability score. YAMSim has a good performance in terms of computational time. However, similar to SSJ, it took up a large average percentage of the CPU, especially at smaller input sizes. SymPy was comparable to the aforementioned frameworks for smaller input sizes, but was found to have a higher rate of change in regard to increasing input sizes, scoring significantly lower for the larger input sizes. It furthermore scored best in the usability comparison. JavaSim was found to be significantly slower across all input sizes, but utilized a much lower percentage of the CPU. All aforementioned frameworks were found to have a linear development in the relationship between increasing input sizes and the time needed to process them. Further, each framework's utilization of the CPU and their respective performance on the tested input sizes was found to be corresponding, with the exception of YAMSim in the smaller intervals, likely given the increased overhead of the framework. Lastly, SimJulia scored the lowest in both performance and usability. It was much slower under the given load range and showed internal variation in its performance. Further, SimJulia's documentation was often incomplete or outdated, leading to a challenging user experience in implementing the selected model. Let's have a look at the summary. The aim of this study was to identify open source modeling and simulation libraries and compare them on parameters related to performance and usability. 50 frameworks were initially considered, which were filtered down on the basis of the following parameters: nature of domain, openness of license, popularity, and how recently optimizing or modifying updates were released. After the filtering, 5 frameworks were extracted for further testing: YAMSim, SymPy, SimJulia, SSJ, and JavaSim. Performance and usability tests were conducted and the frameworks were compared. Thank you for your attention and feel free to ask me any questions you might have.